Swayam Prabha. Digital India. Educated India.
So today we'll start with evolutionary multi-criteria optimization, where we're going to use the evolutionary optimization which we talked about before and use it to modify it to solve multi-criteria problem. Okay, so first I'm going to show you these classical methods we talked about, but what are the difficulties with that, like weighted sum, epsilon constraint, some early EMO methods and some current state of the art, how do you handle constraint, and probably an applications study. Okay, so first thing is this definition of domination, which we already talked about, right? But domination word, this word domination, let me see if this, yeah, this domination is coined by the evolutionary people, so it is not there in the classical sense, but it's basically same as x1 dominates x2 means x1 is better than x2. Okay. So if this is the two things that you have to satisfy in order to say x1 dominates x2. So x1 cannot be worse than x2 in all objectives. They can be equal. In some objectives x1 has the same function value as x2, but x1 cannot be worse. So and then x1 has to be strictly better than x2 in at least one objective. So if we take for example solution 1 and solution 2, and let's say I'm maximizing f1 and minimizing f2. So if I'm thinking is x1 better than x2, okay, so let's see, 1 has a better function value because I'm trying to maximize than 2, right? 1 also has a better value than 2 in f2 because I'm minimizing f2. So 1 is better than 2 in all objectives. That satisfies the first condition, that x1 is not worse than x2, and x1 is strictly better than x2 in both objectives. So it also satisfies both this second condition. So that means 1 is better than 2. So we say that 1 dominates 2. Let's try another one. How about 3 and 5? Does 3 dominates 5? Okay, let's look at that. 3 has a smaller value than 5. That's enough to say that 3 cannot dominate 5, because this violates this condition, that 3 has to be better, no worse than 5, but we see that 3 is worse than 5 in f1. So that doesn't satisfy this, means 3 cannot dominate 5. You can stop checking anything further. So that may mean, does this imply that x5 dominates x3? Let's check that. So x5 has a better value than x3 in f1 because I am maximizing, x5 has a higher value, but x5 has a higher value than x3 in f2, but I am minimizing f2. So f2, f3 is better. So this is also not true. This is also not true. So in multi-objective this can happen, that A is not better than 2 and A is not better than B and B is also not better than A. So what are they? They are equivalent, and they are called non-inferior to each other. They are not inferior to each other. They put in the same class. They belong to the same class. Okay. So if you look at these 6 members if you have in your population, and if you want to identify which points are we call non-dominated. I think we have the next slide here. Let me see. Yeah. So out of these 6 points, if you want to find which points out of the P, if this is the set P, we are saying which points are non-dominated. That means in that set no other point dominates. So how do you find it? So if you have the population, let's say 1, 2, 3, 4, 5, you check 1 with 2 first. Does 2 dominates 1? We've just seen that 1 dominates 2, but 2 doesn't dominate 1. You see, 2 has a value, worse value than 1 because I am maximizing. So 2 cannot dominate 1. So 2 doesn't dominate 1. Next move to the third one. Does 3 dominates 1? Let's check that. 3 has a better value than 1 in f1. 3 has a better value than 1 in f2. So 3 dominates 1, right? So because 3 dominates 1, I don't have to check with 4 and 5 whether 4 dominates 1 or, as long as one of the members dominate another, that member cannot be part of the non-dominated set. So this cannot be part of the non-dominated set. Now let's move to 2. I've already said 1 dominates 2, so 2 cannot be part of the non-dominated set. Let's do 3. Is there anybody dominating 3? Now when you are maximizing F1, minimizing F2, there should not be any point in the 4th quadrant. When you are minimizing both, then there should not be any on the 3rd quadrant. But here, if there is any point here that has a better value of F1 and a better value on F2, so that's better than 3. So because 3 doesn't have anybody here, nobody dominates 3 in this population. So 3 is a member of the non-dominated set. So if I have a non-ND set, I already got 3. Let's move to 4. So in order for 4 to be in the member of that set, there should not be anybody in the 4th quadrant of 4. Is there anybody? Yes, I see 3 and 5. So 4 cannot be. Let's move to 5. Is there anybody who is in the 4th quadrant of 5? No. So 5 goes there. That's it. So this is how you identify the non-dominated set of a population. So P dash is this. Okay. You need, if there are n points, you need n log n complexity computations to find the non-dominated. First of all, you don't know how many of them will be there, but this process that I described, you can make it little faster and you can have n log n. If for m equal to, for objective equal to 2 and 3, you could do this. If you go to 4 onwards, okay, then you have a power here to the power m minus 2. So it's just every time you add an objective, you increase the complexity by log n times. So it's a very fast way of doing it. Okay, so this is one thing about a set of few points and identifying the non-dominated set. Another thing about the Pareto optimal set. So what is that? So I may have, so this could be my, you see this yellow part, this could be my overall feasible space like Z that was talking about, right? And I'm maximizing this one and I'm minimizing this one. Okay, so where is my Pareto set? As I said that there should not be anything on the 4th quadrant. So take all the points, take this point, there is nothing on the 4th quadrant, so this is part of the Pareto set. So you will see that this red line is the Pareto set for that yellow part, right? So now we have few representative points here and the oh sorry, I forgot the 6th one. 6th one also belongs here, belong there. So basically here is a front, that's called the front number 1, that's a non-dominated front. That is different from the Pareto set, because in order to have the Pareto set, you need to have every point on the search space in this set. I only have 6 points here, but you need to have infinite points and then apply this logic, then you get the Pareto. But that's not the recommended algorithm. We will have much faster algorithm to get to the Pareto set. But this is the way you can visualize. If you have the entire feasible set and you apply this non-domination principle, then what you are going to get is the Pareto set. Okay, I want to go back to another thing here. So I've identified 3, 5 and 6 as the non-dominated set. Nobody dominates them in my set. If I temporarily discount them, I'm left with these 3, right? I can again apply this non-domination. I'm just not going to consider 3, 5 and 6 anymore because I've already classified them. So does anybody dominate out of the 3? 1. Let's look at his 4th quadrant. Neither 4 nor 2 belong here. So yes, this is belonging to the 2nd non-dominated class. So I call this maybe P1 dash. If I do P2 dash, now I am finding that first one belongs there. How about second one? I do a 4th quadrant, I see 1 and 4 belonging there. Any one would be enough. So 2 cannot belong here. How about 4? Yeah, 3, 5 belongs, but then I am not considering it, right? So between 1, 2 and 4, 3 doesn't, nobody is here. So 4 is also part of it. So this is called the non-domination of class 2. This is non-domination of class 1. And then the third one, here is just one left, so it will be 2. So in some sense, 3, 5 and 6 are the best solutions of my population. This little population I have, 3, 5 and 6 are the best. Next best are 1 and 4. and the worst is second. And you see, if you line up this way, you can call them as front, okay, and this is the front. You now see that if you emphasize 3, 5 and 6 in your GA more than you do 1 and 4, more than you do 2, then you are setting up a direction for the algorithm to move towards the Pareto set. So this is the first step of thinking of an algorithm, that what you should do so that you get towards the Pareto set. So one thing is getting towards the Pareto set from the search, the other thing is maintaining a diversity, right? I cannot just converge everything here, then I have not found the most part of the front. So I also need to maintain diversity. So we'll have to talk about all those. But before I go to an algorithm, let's see, let's 4 scenarios when I have 2 objectives. Let's say I'm minimizing F1, minimizing F2, okay, both are being minimized, and here is my Z, here is my feasible objective space. Again, remember that I have a variable space here, x1, x2, x3, and there is a space here, every point is mapped here, and this is how it looks like. Remember that cantilever beam I showed you, right? There is a variable space and there is a objective space. This is the objective space. Every time I have F1, F2 means it's an objective space. But there is a implied variable space from where I am getting these blue points, right? And these are all feasible points for the variable space coming here. Okay. There can be holes also inside, but let's say we take a simple situation here. Now when I am minimizing F1, F2, what did we discuss? Every point will be Pareto optimal if there is nothing on its third quadrant. So this red line will become the Pareto set. Let's now say another situation where I want to minimize F1 but maximize F2 instead of minimizing F2. Then there should not be anything on the second quadrant, which means there should not be anything here, because here will be better than this. So my Pareto front moves now here and here, as we have seen on the other example, because this point is going to dominate, this point is going to dominate this entire thing, including anything over there. So, so none of this can become the Pareto set, right? Okay. So same thing. So no, this point is going to dominate this entire thing. This point is going to dominate this entire thing. So this gets dominated, all this part gets dominated when you have this point. So this cannot be part of the Pareto set. So the next one will be right there. So this and this together is my Pareto set. So you see, Pareto set can be disjointed. It depends on your nature of the objective space. Next, let's look at maximizing F1, minimizing F2, the one we just did, and it is this corner. And when you are maximizing, it is this corner, because nothing should be on the first quadrant. So depending on what you do, which one you minimize, which one you maximize, it's always a boundary part of the feasible objective space that becomes your Pareto set. Here it is this boundary, here it is the other boundary over there, here it is this part, and here it is that part. Okay? Not necessarily every part of the boundary has to be Pareto set. Of some combinations. For example, this part will never be Pareto set for no matter what you optimize, what you minimize, what you maximize. But the opposite is always true. This point inside can never be a Pareto solution. Okay, it always have to be boundary. Okay, clear? You can extend this to higher dimensions. Like if you have a 3 objective problem, then I can imagine there is another axis projecting out of the plane here, and now instead of a planar Z, you have a solid Z, and now you have surfaces, and then some patch of the surface will become your Pareto set. It's hard to imagine, but that's what happens for higher dimension. I actually mentioned this already to you. Now we get to this ideal multi-objective optimization process, which is using evolutionary method. You have the original problem that we discussed. Now here you don't ask for W's, all the weights, how do I scalarize, how do I have epsilons, never ask. You just take the problem, apply a method. This is the EMO methods that we'll be talking about today. You are supposed to get a nicely distributed set of Pareto solutions, as you see here, okay, without any bias. So you start from one end, go to the other end with uniformly distributed set of points. That's our goal. Once you've done that, so this is the optimization step, right? Once you've done that, now you need to pick one from it, right? Now you need to sit with decision makers then and get their preferences and then pick one solution from it. This is how all the auto industries and the consumer goods industries like kitchen appliances you find in a departmental store, lots of varieties, some that's costly, some that's less costly but have different functionalities. So they have done it for us, they have designed these Pareto solutions and kept it on display. As a user, decision maker, this is what we are, decision maker, we go and look at our pocket and look at our need and then pick one up, right? Maybe our friends help us choose one. So oftentimes these are group decision making that you do even in industries and pick one up. So since you will be picking one up at the end, this question always comes, why do I have to find all of these solutions? Because it looks like it's a waste of computational effort to find all of these points and eventually pick one. Okay? But I want you to understand it in a different way, in many different ways. First is, imagine you don't know, so in that case you don't know these points, right? Your goal is to go and pick one solution, and I could do a weighted sum, I could do epsilon, and you don't see this line. It could be this point, it could be that point, any point there, and you have no idea what other alternate solutions there could have been, as if the automakers have all produced one single car. Like before 1983 we used to have only Ambassadors and few other, right? You had not much choice, but after that when the market opened, a lot of foreign cars makers have come, and now we have a lot of options. Sometimes it's not good when you have a lot of options, but to a lot of people that's good, that because you can now choose whichever, it's more flexible. So here you can actually see all these trade-offs that we are talking about. Like if I am choosing this, and these are two neighboring points, so how much I am sacrificing on F1 and how much I am gaining on another. So this kind of things I could do. Like so this could be cost, this could be something else. So I can actually compare how much more money I have to spend if I go for that car, not this car. And then how much safety, how much other things I am gaining by paying that extra amount. Is it worth it? So all these we can analyze in our mind, okay? And then decide which one is best for me. If you give me one solution and no other alternate solutions, I have nothing to compare against. So either I take it or leave it. So I think to human mind, this idea of a computer giving one solution and whether you take it or leave it approach is all gone, long time ago gone. We as a human like to have alternate solutions and let us be the decision makers. So humans are back into the loop with this kind of a concept. This one resonates very well with industries. I'm talking to lots of industries. They come to me because of these aspects of multi-objective optimization, that we are giving them not one solution but a handful of solutions. Again, I'm not giving them 50 solutions. That will be too much for them. In fact, recently we did a study with some behavioral science people from Finland where about 50 students we hired, and we put them with these EEGs and all that, and their heart rate and everything, their eye tracking, and we give them a lot of experiments to do. So we sit them like about 2 hours with a gap in between, and they look at various things with 2 objectives, with 5 objectives, all the way we went up to 10 objectives. And we note down what are they doing, how much time, response time they have when I have 2 things for them to decide versus 4 things in one package to decide. That means they have to look at, they have to compare one here with one other there. Obviously, as the number of items go up, the time goes up, but we also look at their eye movement. Are they comparing, or are they looking at one thing? Are they focused on one thing? A very interesting result came out. So what happens is, as you increase the number of objectives, okay, the time complex, we are basically, all these metrics we are defining something what is known as mental burden of decision making increases like this. When it's about 6, it stabilizes. Slight improve, but kind of stabilizes. What happens there? So this was very interesting to us, that what happens when you have 1 to 2 to 3 to 4 to 6 and we went up to 10, right? Somewhere there is a kink. It so happens that this is when you have 5 or 6 things to look at simultaneously, it's so much burden on human, we look for shortcuts. So the experiment was done is we give them movie tickets and in one packet a 6-pack of Coke can, some subscription to Amazon or various things, we have a package, okay, and then another package which are different, there can be some things common, and then we do it 2 objects here, 2 items and 2 items, very easy they could do, 3 items, and that's how it increases, right? When you have 6 or more items, they are actually looking for their favorite things, okay. If they find it, they don't look at any other thing, okay. So that's called heuristics in that literature, shortcuts to me, okay. I think the same thing may be happening if you are framing a 10 objective problem from industry or from your area, and you have to make these decisions, 10 things you have to look at before deciding which is better. Human minds cannot spend that much effort, right? So we also need to look at this cognitive load that we have, okay, to do this kind of decision making. So far these have been ignored, okay, and we say, in fact these days our best journal, if you want to publish a paper in EMO, unless you have 5 or more objectives, like best if you have 8 or 10 or 12 objectives, it will not going to be accepted. The reviewers will send it back saying have more objectives, and so this paper may address that and say, hey, let's not ask always more and more objective, because people find shortcuts to do. They will probably not look at this 10-dimensional space. But more and more such studies are needed to really confirm this, also from practice, that one paradigm is until about 5 or 6 objectives that human mind can handle. Another thing, what we should do for beyond that, because the problems will come. We often get problems with 11, 13, 14 objectives. I will show you one 14 objective problem later. But this thing will come, but decision making involves human, and we also have to look at the limitations of the human. So anyway, but this is not an easy task also to get from these solutions back to one. I am not undermining that, but lot of people in the computing area, computer science, I should give you this example. So these software, search-based software engineering, software engineering is a big area, right? But search-based is using optimization to find for faults in a code. Before you release a code, you should look for any input setup that's going to screw up your code. It's going to go into a loop, infinite loop or something. It may not be obvious, but you can apply optimization for that. So optimization used in a negative way, but a lot of people, that automatic software testing people, they do this. So there is a whole bunch of people that are working in this now. They have their annual or maybe biannual conferences. So in one of the conferences, they invited me to give a talk on multi-objective, because they were planning to do that. Is the microphone working? Yeah, working, right? Yeah. So so they were planning to use multiple criteria for arriving at those things. So I gave a full hour talk, and then there was then question session for another 10-15 minutes. So there was a student from UK, a PhD student finishing up in this area. He stood up and he asked me a question that, so I will give you an example which I showed them later, okay, it's coming, but it's from practice, very practical, with 14 objectives. And there I was also telling them how to make decisions. So this part is algorithmic because it's optimization. This part is more like heuristic based, and now you come with your choices, whether you like this objective more than that objective. So you need to talk to people, interview the decision makers and all that. So I gave a brief overall description of that. So he stood up and said, are you asking us to go out and talk to people to solve problem? First I didn't understand what he said. So what he meant is, are you asking us to go out of our office and consult with people to see whether you like this solution or that solution? I said, yes. Do you think you can solve world's problem sitting in your office? A lot of computer science people think that way. Okay, they can solve everything sitting in their own corner. That's never true, right? All those of you who are in industry know that very well, right? But that's interesting. But that was easy answer for me. But then he asked me an interesting thing. He said, but I'm finishing up my PhD, and I had to never take a course of how to talk to people. That is true, right? Any of you taken a course on survey, some kind of surveying, where you have to go with your notebook and talk to people on the street, or maybe knock some doors and housewives ask, what do you like, how much water you use, and no? But those of you who are in civil engineering probably have such a course, you know? We didn't do? Practically. So when you leave from here, go a company, you know, within a year or two they're going to send you to do this kind of survey. But many of our courses are not geared towards that. So I think we should have, for every one of you who are problem solvers, we should have at least a part of a course where you do some surveying, gather data by talking to people, maybe calling on phone, get some data, and then analyze those data. Otherwise you are not seeing that part of the flavor. Do you know how to talk to an unknown person? How do you start? So you meet somebody on the street and you like his face, you said, okay, I want to talk to him. So how do you start? What do you say? Because it could be annoying to him. First thing you have to see is how busy is that person. If he's going very fast, don't bother, right? But looking at the face, you can figure out, is this a guy who can be little cordial to me, or angry looking person? So don't forget. So there are a lot of things that is psychological, and engineers don't have that angle. And they are poor judge of people's faces and people's mind. And this requires skills, but there are a lot of tricks which you can do. If you have an opportunity, but you have a social science department here, I suppose, right? Part of the humanities. If anybody is teaching any course like that, or outside the campus, if you find an IIT Madras takes that kind of credit course, please do that. It's going to be very, very helpful. Something that is entirely different than computing. Just psychological, I would say, kind of course, and surveying kind of course. These are very useful if you want to be in this particular area. I have learned it little bit by working with people, but I also didn't have an opportunity to take such a course. But this will be a kind of much fuller education that you are going to get, not just computing engineering techniques, but also the human aspect of it. Talking to people like, so my wife, for example, teaches a course like that, communication skills. It's very, very popular in MSU. Okay, she takes only 25 people. The first day it gets filled. Okay, she does a lot of elevator speeches. So you are stuck in an elevator with someone. It's very odd to just stand still and not talk. Okay, here of course it's the culture. You don't unnecessarily talk to strangers, right? That's what our parents taught us. But in US, Europe, Europe also a little bit like this, but US is not that. Even if you are crossing someone you never met on the street, you just say, how do you like the weather today? Or something odd, something just to have a conversation. If you are not saying that, you are rude. So when I came back from US and joined IIT Kanpur, I had that habit of saying something to passing by people. My colleagues, so they always put their heads down and walking, and I say, how are you today? He looks at me, he stops, and he says, I'm fine, but why are you asking? You know, all kinds of things. And I said, wow, I just said hello. And then from there on I stop saying. So, you know, it's a cultural thing, but I think it's not bad, just to be a little human, show the human side of it, right? That's what I mean. And you can start here, right? Today afternoon, tomorrow morning, if you meet one of the persons here and they say hello. Okay, it doesn't take much, right? But that's a good start. So these things, when you go from here to there, it requires all that kind of skill. You are in a group working with your boss, maybe your subordinate, and it's a group is basically comes with lots of different diversity. How do you start a communication? Because you always have to impress your boss, right? And then you also have to be a little authoritative to the persons below you. How do you start a conversation? Do you agree on everything? Or do you also show that you have a mind on your own? Your boss will like that. But sometimes we think, no, we should always agree with our bosses, right? Otherwise we are rude to our bosses. A lot of boss may like that, being always agreeing, but not everyone. You should always show that you have a separate mind which is logical, which can be good for the company and things like that, and then everybody appreciates. I'll tell you that. So where do you say what so that the information provided is useful in making such decisions? We are not going to go in this course in details of that, but what I'm telling you is a flavor that when you are in this decision making domain, all these human aspects become important, and you may have to take some courses or at least have some exposure on those. Okay, so these days a lot of algorithms and methods are coming out where we don't first do optimization and find the whole set and then make a decision. This is a two-step process, but rather we have a diagonal step where we do few iterations of optimization and we get some Pareto, not Pareto then because we haven't converged to the Pareto set, we call it non-dominated set. Like, if I go back here, this is the Pareto set because this is my entire thing and this is the best possible solution. These are Pareto optimal solution. When you give me these 6 points, here is my non-dominated set. Okay, that's different from the Pareto set. So if it's not Pareto, we call it non-dominated. There is a trade-off between them, but it's not Pareto. Okay, so so you get this non-dominated set, you pick 2-3 points, go to the decision makers and say, so far I've got this. Can you tell me something about which one you like, which one you don't like? Based on that information, you do some calculation. I'm going to show you one that we've done, and then you come up with some kind of heuristics of what they like, what they don't like, and put that part of heuristics back into your algorithm. So now if this was your Pareto set, and let's say you got these few points here, and they told you they like this one more than any other, and maybe next one is this. So you got some idea that maybe I need to go this way. My Pareto set will be kind of like this. So these are dominated. So use that kind of information, and next time you find only here. Next time you find only here. Like this, you are going to converge to only a part of the Pareto set, not the entire Pareto set. Because the decision makers have driven you that way, have told you what they like, what they don't like. So you may have to go in few sittings like this. Eventually when you come and converge to the Pareto set, it's only a part. So that's kind of the not finding the entire thing and making a decision at the end, but decision making along with optimization. This is the future, I think, and we've just started with some ideas there, but there are much more needs to be done there. Okay, so let's stick with the two-step process. First we are going to find the whole Pareto set, and then we're going to defer the decision making. So in that case, if you get, so this is my Z, if this is the entire set of solutions I found at the end of my algorithm, are they good? I see that there are good diversity, but none of them is close to the Pareto set. So in that sense they are not good. How about this set of yellow points? They have all converged to the Pareto set. All are optimal, but they don't show me a major part of the Pareto set. There is no diversity. So no convergence here, no diversity here. Both of them are bad. Okay, so if an algorithm is doing any one of them, they are not as good. But it's the one that are in the black have a good convergence and a good diversity, almost uniformly distributed. That's what we are looking for. So any algorithm we are going to design should be able to do and find these black dots of points, right? So convergence is important, which was also important in case of single objective, but now I have an additional goal that I want to find as diverse a population as possible. Okay, so why population approach? Why evolutionary method for doing this task, that convergence with diversity? Why? I have a population. Let's say this is my population. I've got one super individual here, came from crossover, mutation, whatever. Next generation, this will be the best solution, right? This is going to cross with that guy and probably create something here. This is going to cross with that guy, probably create something here. This is going to cross with that and probably create something here. So suddenly this solution can bring things that way in a parallel manner. Okay, so that kind of implicit parallelism that our methods have is kind of helps getting to the Pareto set much faster. And I'm going to show you now how evolutionary methods can find multiple solutions simultaneously, because that's an important part of getting to the multi-objective. Okay. But before I do that, I think I'm showing you some results with NSGA2 here. This is one problem where there is a non-convex Pareto front. So weighted sum will only find the two extremes, nothing in between. Okay, but our method is able to find this. This was the result that found by epsilon constraint, a little better version of that called normal constraint method, NCM. So this is with NCM. This method, you see, it found some weak, but our method doesn't find the weak. Here is another problem where there is a global Pareto front here, but the NCM got stuck at the local, but our method can find the global. This is another one with three objectives. NCM got stuck. This was the Pareto set surface, but it got stuck here, as you see, after 100,000 evaluations, but our method goes and converges there. There are some weak spots which we're going to fix. I'm going to show you some fixing of those later. Okay, so this is some evidence that a simple GA code without any parameter update or anything can solve various kinds of problems. Okay, so if you think of these two goals that I've talked about, what is there needs to be changed. This is the GA loop that I showed you. Initialization, counter, initial counter to be 0. If termination condition not satisfied, you evaluate them. Assign fitness, selection, crossover, mutation, increment counter go into the loop. I showed you in a flowchart, showed you in a pseudocode. Now here is a flowchart. It's a similar thing. When you evaluate now with multi-objective, for every solution you have F1, F2, so on and so forth. It's not one F anymore. So how do you take that and assign one fitness? Because selection still needs to be done with one fitness, right? That is the important thing that we have to do in multi-objective. Two things we have to keep in mind: diversity and convergence. Now if you look at diversity, this can happen in two spaces now, because I have a population of X, right? X1, X2, this is my population. I also have F1, F2, F3 for every population member. I also have F. So the variable space and the objective space. This is the variable space, this is the objective space. If I take all these 10 different solutions here, if I look into the variable space, they may look like this, which means this one is isolated, this one is isolated, and there are a lot of crowding here. If I look at the same solutions in the objective space, they may look like this, where there are a couple of them isolated and many of them are clustered together. Most likely in practical problems, these are here, and this may be going there and this one may be going there. But in some very nonlinear problem, it could be one of them is gone there and one of them is gone here and this one may have come here. It depends on the nonlinear functions that you have, right? So it need not necessary that the isolated point in the decision space is an isolated point in the objective space. Okay, just 2 days ago, I had a meeting with GM and we had a problem like this. We noticed that it's a engineering design problem, but it's so nonlinear that the points in the decision space which are close here, but they're very much diverse in the objective space. So it depends on the nonlinearity, right? It can happen. So now you have to decide which space you want to do the diversity preservation. You want to preserve diversity here, which means if I find the Pareto set, I will have a very nicely distributed set. Or they could be crowded here, but here I see a nicely distributed set of points. What's the difference? In decision space, if you have a nicely distributed set, means these solutions will look different from each other, because decision space is all about how the solutions look like. This is the performance space. Now if you get uniform distribution in the performance space, then you're saying, oh, I have good options with different performance metric values. They are not all very close to each other. Which one do you like? Do you like to see solutions that are usually very different from each other and I don't care how their performance is, or I want to see the solutions, I don't care how they are, they could be close to each other, but performance wise they are good distribution? You need to decide that first. We also have some algorithm where we try to maintain diversity in both spaces, but those are very uncommon. Most EMO algorithms are trying to do this, okay, because again, mostly populated by computer science people, they don't care about the variables, they care about the performances. but engineers, I believe, should care about the decision space. But doesn't matter. Usually, as I said, there is a one-to-one. If this is diverse here, this is also diverse on the other space. Okay, but you need to know that part. It's a kind of hodgepodge I'm doing here, but let's do. I probably had a purpose of why I'm doing this way. So how all these have started? Yeah, go ahead. Question.
Previous slide.
Yeah.
We need the decision space also. If they are close together, only the solution can be robust. Right?
Robustness is completely different concept. Robustness means that if I perturb, so let's say this is my solution goes here, okay? Let's take a solution that goes to the Pareto set. So let's say this one comes here. When I evaluate, this comes here. This is one of the Pareto solution. If I take a simple small ball around it, that means neighboring points, I take 5, 10 points, evaluate them. If they are all over the space here, let's say when I evaluate, they're all over here. That means it's very sensitive. If you evaluate a neighboring point which is close to a current point or current optimal point, when you evaluate, they are all over. Their objective values are very, very different. Then it's called a non-robust solution. It's not robust. But if this point comes here, and if I do the same ball here, and I evaluate solutions and they are staying right here, that means it's robust. So sometimes, so this is, so we'll talk about it maybe briefly. This is your Pareto optimal set, but if this point is not robust, if you find the robust front, that means a set of points with robust solutions, it could be that it go like this. Your front goes like that because this part is not robust. So your algorithm is not going to find optimal solutions, rather find robust solutions. So robustness, I mean here, is in a different way. It's more of the sensitivity of how sensitive is your objective function with respect to perturbations in the variable space.
So I was asking, for example, if we have a number of solutions which are close by in the decision space, it's good because the values don't change much in the objective space.
Yeah.
Engineering decision making.
Right. So why would we like a diverse solutions in the decision space? Because if you give me 5 solutions, let's say these are engines, 5 engines you have designed for me, and telling me these are Pareto optimal, I don't want to have or like to have 2 solutions that look exactly the same with slight differences in them. To me, they are all equal. If you show me different technologies, different geometries, then I say, oh, they are different. Now I'm interested in seeing what are their performances. Okay, like maybe what is the weight, and maybe what is the combustion thing, some property of that. But if it's iota difference from one to each other, I know performance is also going to be very small difference there. I'm not interested. So when I say alternate solutions, I'm actually thinking of some change in the design, so that I'm kind of explored my design space. I found variety of solutions with lot of differences in them, right? Okay, so this field started around this guy, Vega, his Dave Schaefer. He suggested Vega in 1984, but his algorithm did not work. He did his complete PhD thesis, but you have to think of 1984. There are not many, no multi-objective algorithm using evolutionary was available. He was the first who thought maybe with the population concept we can find a Pareto set, but his algorithms ran, but they apparently have Pareto solutions, but then they all converge to 1 point or 2, 3 points. He tried few things, but he could not do this. Goldberg came in 1989 in his book, and he said he was missing, Dave Schaefer was missing one thing, which was the diversity preservation. Schaefer didn't realize that we need to do this. So Goldberg did that, and then these 3 groups of researchers, NSGA was developed by us at IIT Kanpur when I was there, and MOGA was this guy Carlos Fonseca. He was doing his PhD in UK, in Sheffield, and NPGA was Jay Forn with Goldberg. They developed NPGA, all based on Goldberg's ideas, okay? And all 3 of them worked. So you have to give a lot of credit to Goldberg saying, identifying what was missing in Dave Schaefer's work. So from then on, we established that we need to have convergence, we need to have diversity preservation. Lots of new algorithms came out, and you can see how it kind of went. These are all the early algorithms that you see. I'm only going to talk about, I think, probably even not that, but this is nobody is using this anymore. But this was the first algorithm we had. The reason why not people use any of these anymore is that all of them have some parameter. At least one parameter you have to set. Okay, so let me skip because this didn't work. But let me go to something very important, which is common to most of this diversity preservation thing. So before 1989, when Goldberg suggested that we need to have diversity preservation, this work was already done by him and one of his master student called Richardson. They've already done that, called niching. What is niching? Let's talk about that. So let's say I have an objective function that looks like this. Okay, what is it? There are multiple global maxima. So there are these two solutions are giving me the same optima. There is another local one. Maybe they are equivalent, or maybe this is a slightly lower than that. So there are multiple optima, and we often see that. I showed you a function with 4 optima before, right? Now one thing is, if I apply optimization, point-based methods, I start with some point and it's going to climb up the hill and it's going to give me that with gradients and everything, then we'll get stuck. If I want another one, I have to start from a completely different place and maybe we find the other one, right? Now if your goal is to find any one of these local or global maxima or minima, then it's the usual thing we do, right? You can use any of these algorithms we talked about. But multimodal optimization is when I'm interested in finding multiple optima, local, global, simultaneously. In one run, I want to find multiple. You can say, okay, I'm going to split the run. I'm going to first find this, then find this, then find this in a systematic manner. And once you find this, there is a way you can squash the function so that this is no more of interest, and you could do all that. That's also multimodal optimization. But your ultimate goal is to find not one but multiple optimal solution. Does that make sense? So if you do that, if your goal is that, Goldberg and Richardson came up with this concept with the evolutionary method, the genetic algorithm, with this concept of niching. What is that? That says if I have a population of solutions, so these are x vectors, and I am solving that function, for every solution, okay, every individual, I will look into the whole population and find my neighboring solution who are close to me in x space. And then if it's exactly on me, if I have another solution exactly like me, so same x, then that solution has 100% share on me. If it is about 50% away from me, now we can define what is the 50% and all that, then it has 50% share on me. So like that. When it's more than sigma, then I have no effect on it. It's too much different from me. So as long as you are within sigma, and sigma is that parameter I was talking about, you have to set, then you have some effect on each other. This is exactly what goes on in natural niching process, where you have animals, humans, birds, amphibians are all co-surviving simply because we have shared the niche, which is shared the resources, which is like the land, for example, or the food that we eat. They are different. We kind of agreed that, okay, we are going to live here in cities and urban areas and rural areas. You live in water, you live in jungles. We don't go and interfere with you, right? And that is how all of us are co-surviving. Okay, as we more encroach into their domain, there's going to be only one species that's going to stay, right? But as long as we share it. So Goldberg's idea was that we first identify in my population who are similar, and they have to kind of share their fitnesses, and others that are similar, they have to share their own fitnesses. And he defined this sharing function. You could have different versions of it, but that's okay. The way it works is that this sharing function value you sum up for all your neighboring points. So you get an idea called niche count. It basically says how many individuals are around you in the population. You then divide your fitness by that number, you get a shared fitness value, and with that shared fitness value you apply selection. Now this idea of Goldberg and Richardson only works with one selection operator, that's called roulette wheel selection or proportionate selection, which I haven't talked about. So there are certain things that I have not talked about, but I'm just giving you here an overall idea. It only works with proportionate selection. So here's what happens. If I have these these 5 or 6 solutions in my population and I am solving a two-peak function. My goal is to find both peaks. You see, I get the x vector from the binary string. If I am doing a binary coded GA, I get the f values which are shown here. Now for every individual, let's say individual number 1, I find the niche count, which says about 3 individuals are around it. When you do the niche count, you see there are about 3 individuals around it. So 2.856. Number 2 also has about 3 individuals around it. Number 3 has only 1 individual. Where is number 3? Here. You see in the neighborhood there is nothing except itself, so only 1. And then 4, there is also 1. And then 5 and 6 almost have 3. So this kind of gives an idea of your size of your neighborhood. Then what you do, you divide this by these numbers, so you get this. Now you do proportionate selection with this as the fitness. Then what happens is, as like this one you see here, this is alone representing this peak. What is the shared fitness? 0.89. What about 6? 6 is 0.295. You see, this is the best, right? So in the next generation, when you do selection with this, this will get 2-3 copies at the expense of some of these. So whenever you have crowding happening, your niche count number goes up, your fitness gets divided. So your effective fitness is low compared to the one that are isolated. So that's the idea, that's the balance that's being maintained, and this can go on as long as you run it. So you'll always run, if you run, always you will see equal number of individuals around each of this peak. So that's the idea of the sharing function. If you don't do sharing, you see all your population goes to the global peak in a 5-peak function like this, which I simulated. But if you do this sharing function, you see there are individuals in all peaks, and you can keep on running it. It's going to be there. Some of these bad ones come because they do crossover and produce some of these. So there is an idea of mating restrictions which will help you eliminate those. But that's the whole concept of niching. I show you here on a 2-variable function. You see there are 4 peaks, but this is the feasible region. When I implement this niching, you see the population. So these are the red ones. I think at some generation 10 or so and generation 50. I'm sorry, this is the initial population, these gray ones. Then they all enter the feasible region after a few generations. And then when you keep running for a while, you have subpopulation within your population. Some of them are here, some of them are here. You see how they are maintaining, and you can run it for 100 generations, 1,000 generations, they will still be the same. Okay, that's the power of niching. If you don't do niching, some of them will go to, all of them will go to one of the peaks. Which one I cannot tell you. It depends on some kind of they call drifting. So it depends on initial population. If you had more copies in one, there is a natural push that other populations go to that one. Okay, so NSGA I'm going to not talk about because this is no more used, but it has this parameter sigma that you have to set. But this was the first thing we did based on Goldberg's idea in 1995 with my master student Srinivas. Okay, the drawback of these methods is this sigma. Other drawback, or a parameter, other drawback is none of this had this called elite preservation. What does it mean? Elite preservation is when you are going generation T and going to generation T plus 1, we do selection, crossover, mutation and create T plus 1, right? If you are not ensuring that the best solution from the previous generation is always passed on, okay, then you may have a population at a generation which is not as good as the previous generation because you have not copied the good ones from the previous one, and that's not good, and that's called elite preservation if you're doing it. So some of the early algorithms we did not do that complication, okay, and we had some issues with that. So now the later generations, which I call generation 2 algorithms, we have this elite preservation, plus we try to take away any parameter that it has. Okay, so elite preservation becomes an additional goal along with convergence to the Pareto set and diversity maintenance. Okay, okay, and there are lots of algorithms so far, but these are, you see, dated already back quite a bit. I'm going to talk to you about maybe 1 or 2 here, NSGA2 and maybe SPA and PACE. Okay, so what is NSGA2, which is, you know, a lot of people are using these days. This is a old slide. This has now become about 50 plus Is it 59,000? Maybe 59K citations for this paper. So what it does, and a lot of commercial codes have implemented it also, and I'm not a part of any of these. 2 and 3 objective problem, you start from this inside region, randomly initialize, and the points will come and go to that patch of the Pareto set. I told you, like, it will always be a boundary part, and it represents that boundary very well. So that's the NSGA2, but let me show you a bit more detail. We have the parent population at generation T. You apply selection, crossover, mutation, you get QT, same size as PT. Now what you do, you combine them into one, call this RT. Do a non-dominated sorting. What is that? First find the non-dominated set. Remember the 3, 5 and 6? So that's here, 3, 5 and 6. Those are the best solution in this entire population. Then temporarily discount and do one more time, discard. Okay, so then you discard them and do one more time, you get the second class, then third class, and so on and so forth. As you are going down, your solutions are getting worse and worse and worse. Now remember, from this 2n population, where n is the size, population size, I need to have n member. So which n I'm going to keep? So this one is the best, so I keep it. Second best, I keep it. Like that I keep doing. A point will come when I cannot take the entire set, because it's going to increase my population size and I don't have an algorithm then. So that means I need to be picky from here. Which one I use is decided by an operator called crowding distance. So far what I discussed is we are giving importance to convergence. If you pick this F1, F2, you are basically preferring, the first set, then the second set you are preferring, right? So you are kind of saying that go this way towards the Pareto set. But we haven't done anything about diversity preservation. Here is the chance I have. So out of this I need to choose, let's say 2 or 3, then I decide which 2 or 3 I choose so that my diversity of them is maximum. I may have, So let's say I've got these 5 points in my last set, this set. I have those 5 points, 1, 2, 3, 4, 5, right? These are 5. Which 5 I should, and let's say I have slot of 3. This one can only take 3, any 3 of these 5. So the question is which 3? That's where this comes in, with crowding distance. The way I do is, we sort them in F1 first, in increasing order of F1. So this is 1, 2, 3, 4, 5. For the 2 extreme, we assign an infinite crowding distance because there is nothing on one side. To an inside one, we look at the one on the left, we look at the one on the right, and we note down this distance. Similarly for 3, we look at one on the right, one on the left and right, and this is the distance. For 4, one on the left, one on the right, this is the distance. Okay, we save them. Now go and sort in F2, all of them again. So now this will be 1, 2, 3, 4, 5. Repeat the process. We assign infinite. To this one we assign this distance, the neighboring distance. For 3 we assign this, for 4 we assign this, and we add these 2, we add these 2, we add these 2, we add these 2, we add these 2 infinity. Okay, what does that mean? That means for the boundary extreme points I have infinite crowding distance. For anything intermediate I am trying to fix a box touching the neighboring points, 2 neighboring points, and I am then calculating what is the perimeter or half of the perimeter of the box. So size of the box is my crowding distance. Now tell me, if I have to pick 3 points out of the 5, which 3 shall I pick so that I have a good diversity of them? So obviously the 2 extremes I am going to pick. So, and then which one shall I pick? Either this one or that one. This one, right? So if I do that, and then what does it? This is having the highest box size out of the 3. You see, this is the highest box size. So what we do is, after this crowding distance is calculated, we sort all of them in the descending order of the crowding distance, and we picked as many points we want from the top of the list. So infinite ones are going to go on the top, and then this, then this, then this, and then if I need 3, I pick the top 3. What if I have to pick 1? I just pick any one of them at random. If I have to do 2, then these 2. If I have to do 3, then these 2 and 3. If I have to do 4, then these 2, third, and probably that one, fourth. Okay? This works great for 2 objectives. For 3 objectives, this concept of fitting a box and all that kind of dilutes a bit, and it starts to show its weakness. But this is a very fast algorithm. This is what is an SGA2 is. So these are the 3 I'm going to pick. Okay, so and those are the 3 which are going to go over there. You have these 2 plus those 3 from here. You have the population. This goes here and repeat. As simple as that. Is there a parameter? No parameter. Nothing we talked about, right? So it's a parameterless, other than population size, crossover, the standard single objective parameters that you need to have. Okay, so if I just go a bit more, because there is an exercise for you to do. Let's say all my parents are with boxes. So you see these numbers 1, 2, 3, 4, 5, 6. Those are my parents, and all the circles are my offspring. I have named them with A, B, C, D, E, F. Okay, and I'm putting all of them in the objective space here. So this is Z, and this blue region, and these are my objective space. So I ask you to do one iteration of NSGA2. What you are going to do? You are going to first sort them into increasing level of non-domination, which means, or rather domination. So the first front is going to be all the points where there is no point in the third quadrant if I am minimizing both, right? So you see 5, what is that one here? 6, and then A. These are the ones, no, this is E, I think. This is the point E. So 5, E, and A has nothing in their third quadrant, but 1 has A in it, so 1 cannot be on the non. So basically you do non-dominated sorting. This is front 1 or class 1. Then you temporarily discount, and you have then B, 1, D, and E in the second class, temporarily discount, and then you have 6, C, 2, and F in the third class, and then finally 0.4 on the fourth class. So first thing is to do is classify points according to non-domination, and this is n log n, as I said, for 2 and 3 objectives, right? So not very time consuming. Once you've done that, what we do in NSGA2, we actually copy the first. So there is population size of 6, right? There are 6 members for A, B, C, D, E, F, and then 1, 2, 3, 4, 5, 6. There are 6 members. So I need to fill 6 here. 6 population I need to fix. So first thing that goes is A, then E, then 5. So that's belong to the F1, and that goes straight. I still have 3 slots left. Now I go to the second front, okay, because the next best front. How many points I have? B, 1, D, E. Already there are 4 points. So I cannot take any one of the third front or the fourth front members because they are too bad. I only can check 3 out of the 4. How do? I apply crowding distance. So I isolate my second front here. Those are the 4 points, and do this crowding distance. You see again, sorting along F1, this will be infinite, this will be infinite, and this one is this distance to neighboring, this one this distance, and then I do in the other. So these are the boxes. So this has the highest box, so it will be this guy I'm going to choose, and then 1 I'm going to choose. These are the 3 I'm going to choose. So this is going to be 3, B, and 1. So these 3, this one, 1, and 3. D is also deleted. So these 6 points go to the next generation. Again, create an offspring population and then continue like this. Is that clear? One thing you have to do though, and that costs someone almost his PhD thesis, is you need to normalize before you compute these distances. Because again, if this is 10 to the power 6 level and this is 10 to the power minus 6 level, you cannot simply add, right? So you need to normalize. So how do you normalize? Frontwise you take the minimum, maximum in F1, F2, and then map so that this becomes 0, this becomes 1, this becomes 0, that becomes 1, and now you compute these distances. That is absolutely necessary, okay? Otherwise you are adding apples with oranges. Does that make sense? The normalization becomes very easy in evolutionary methods because you have a population. You know min max. You can always do a normalization with that, right? Okay. Any question about it? It's very simple algorithm, right? And here is how it works. Starting with those points that are here, you see how with iterations they come, eventually converge to the Pareto set. There is nothing here for it to go. And there are about 100 points at the end we get. And if you keep running, the gaps will get filled and all that, you get better and better distribution. This is another problem where you could get stuck. This is ZDT4. Yeah, there are a lot of local Pareto fronts. See where it's almost getting stuck, and then a better point is found, it moves. Ultimately, this one is the global Pareto set, and they come and converge and then diversify to the entire set. Because we are providing infinite crowding distance to the edges, if this is your Pareto set and you have only come here and not here, this gets infinite crowding distance, right? This gets infinite crowding distance. So this will get infinite emphasis. You are almost accepting it. So that means this is going to create new points this way. So there is always a pressure to go towards the end. So this algorithm is really well thought of at the beginning without any parameter, and that's the reason why this is used so much. The first thing is algorithm has to work, okay, before somebody uses it. And with so many citations, it's not only should work, it should be very, very efficient without any parameter and all that. Because sometimes people ask me, many of my work like this has caught on. People are using like default, and some people ask me, is it by chance, or have you really thought about it that these are eventually going to be highly cited papers? You can never think of that when you work on today, 10 years from now, whether it will be highly cited or not, you cannot. But one thing you can be convincing yourself is, let's address the problem to my entire satisfaction. A lot of people don't do that. They just see what is minimal needed for me to get a paper. You may get a paper, but it's going to not have much life. If you want people to use it, you need to be happy first of all. Second is it serving some part to the community? You need to think that way. How good it is, how generic it is, and then you need to provide a code. These are absolutely essential things. Okay, there are some tricks to become to make a paper highly cited, but it's not in your hand. So you can only do so much, and best for that you need to know the field, what is missing in the field, and then try to address those. There is a reason why there is a gap in that or hole in that field, because it could be tough, and people couldn't figure out what to do. So if you can crack that, then you are generating a new area, a new idea. Obviously, it can caught on, right? Okay, let's look at strength Pareto. How am I doing with time? Yeah, maybe I should. Okay, let's quickly talk about these two methods and then I'll stop. Very briefly, SPA is different from NSGA2, but it's also elitist. I'm just going to show you with this example. Here is a population like we have in NSGA2 also, but they have an external population with all the good solutions in it. Then what they do is they assign a fitness to the external population by looking at how many solutions each of these X in this population dominate, and then based on these strengths of each of these, they assign a fitness to this. And then there is a way to select some of these solutions they call clustering. So when you have those points, let's say there are 20 points you have created and you have slot for only 12, because 12 is your population size, you need to drop 8. Instead of doing crowding distance, what they do is they do a k-mean clustering, which means every one of them is first considered to be in one cluster, and then the two neighboring clusters are merged into one, another two neighboring may be merged into another, and like that. And every time you reduce one cluster at a time, when you hit 12 you stop, and then pick one representative point from every cluster. So that's how they reduce the number. So this is the diversity preservation, and here they do domination based on the convergence based on domination. So when both of them are there, you have an algorithm that works. So you can also think of some ways of combining the two. It's just that SPA2 is little complex. It takes a bit more time. Last one I'm going to talk before the break is PACE. This was done by Joshua Knowles and Dave Korn. They are using evolution strategy, which I briefly touched upon yesterday. It's a point by point method, but they keep a population. So once they create a offspring, they compare with the parent. So if the offspring dominates the parent, like this situation, for example, let me see this situation. If 2 dominates one of the archive member, then of course archive member is deleted and 2 is accepted, the child is accepted. If offspring that is created is worse than one of the archive member, like this archive member dominates it, then it's not accepted and the child is thrown away. Most often what happens is this scenario. You have an offspring which is non-dominated to archive member. So this is neither dominating any of the archive member or doesn't get dominated by an archive member. Then what they look at is, so this member, they divide the entire space into all these grids, okay, uniform size grids. Then they see where is the parent, which grid does it lie, how many individuals does it share with that grid, and how many individuals that offspring share with in the grid. If offspring is sharing with less number of points in the grid, then offspring is accepted and parent is deleted, right? Again, the diversity preservation is here and importance to non-domination is here. You need both of those things in order for an algorithm to work. This is a bit slow, but not many people use it this time, but they have very good citations as well. I mean, all over 5,000.